Howdy, ASTR 103 students. Today is going to be our third lecture in our series. And today's lecture is going to cover the first half of the lecture, the first part of the lecture is going to rehash something that I've talked about in other lectures on my channel, and that is what exactly is science. And so I will briefly highlight the differences between science and pseudoscience and the scientific method, and how the scientific method is used in order to progress scientific needs. It will be an abbreviated version of just talking about science than in other lectures. So if you're curious, be sure to check out my lectures on What is Science and Rob World Episode 2. I believe both of them deal with that topic in more depth. The second half of the lecture will deal with Newtonian physics. We will look at Newton's laws of motion and his law of universal gravitation. And we'll see what the implications of those laws are in terms of orbiting bodies and how one experiences the idea of quote unquote, weightlessness. Well, I hope you enjoy it. I will be recording this in two parts. I will first be talking about science, and then I will have to take a break and come back to this and finish off the second half of the lecture. So there might be a little bit of a jump between those two topics. But again, I hope you enjoy, and see you next time.
Okay. Let's get to it, or something. Really should come up with a catchphrase. I don't know what you guys think. Anyway, so, lecture 3 in the series, Newtonian physics. As the intro stated, before I talk about Newtonian physics, I'm going to talk about science. Basically, just give you a general overview of how we define science, or more specifically, how we distinguish it from pseudoscience. Like, how do we distinguish astronomy versus astrology, for example? And I'll talk about the scientific method and how it's used to progress science. And then I'll talk about Newtonian physics. Basically, just a very brief synopsis of Newton's laws of motion and his law of gravitational attraction, or law of universal gravity. And then I will talk about how how the implications of those with respect to orbits, weightlessness, and tides. For example, I will explain why the moon appears to show, or always shows, the same face towards the Earth. This is one of my favoriteest quotes by Einstein, and it is, "All knowledge of reality starts from experience and ends in it. Propositions arrived at by purely logical means are completely empty as regards reality. Because Galileo saw this, and particularly because he drummed it into the scientific world, he is the father of modern physics, indeed of modern science altogether." What Einstein is getting at here is that science deals with objective reality. It deals with that which we can observe and measure, test, and predict. If it cannot be, if it does not follow with any of these parameters, then it does not, by nature, follow as a scientific endeavor. So how do we distinguish science from non-science, or pseudoscience? Well, simply looking at the definition of science really doesn't help us very much. Science comes from the Latin meaning knowledge. There is a variety of knowledge out there that goes far beyond scientific endeavor. There's emotional knowledge, there's artistic knowledge, there is psychological knowledge, although I guess that's redundant with emotional knowledge. But hopefully you get the point that I'm trying to make, is that science is not the end-all be-all of all knowledge. And so it really does not help us to define science, or really look at science in that way. Before we can really look at the hallmarks of what does make for scientific inquiry, we need to have a common playing field. We need to start with a common set of terms. And I like to do this pretty much with any conversation that I'm having with someone, particularly when terms might have different meanings based on someone's perspective or someone's life experiences. I always like to start to define certain terms so that we know what we're talking about when we talk about certain things. Scientifically, a fact is an observation or measurement, and this is invariant to who is doing the observing or who is doing the measuring. I am 6'1". That is a fact. It is I am 6'1" if I measure myself. I am 6'1" if you were to measure me. I am 6'1" if ET from Alpha Centauri were to measure me. That is an observable fact. A hypothesis. A hypothesis is A, an educated guess that B, predicts future events and can be tested. So the 2 points really that I want to get to is that A, it is a educated guess. It is a guess based on previous observations, previously observed facts, and previous knowledge of that phenomenon to guess what something will do in a future date that can be tested given the equipment that we have or potentially the equipment that we will develop in the future. That is a hypothesis. If it cannot be tested, then it is simply conjecture. It does not really fall into the purview of scientific inquiry. A law. A scientific law is an explanation of a single phenomenon or certain phenomenon, usually in a mathematical form. For example, gravity is a law, as defined by Newton. The universal law of gravitation defines a mutual attraction between two masses at a set distance. Based on that formulation, you can calculate what the force of attraction is between two objects of any mass at any distance, and then you can predict where that motion is going to take those objects anytime in the future. Now, the most contested term that people seem to find is theory. Now, here I'm going to go to dictionary.com. The first two, I'm going to take the first and the sixth definitions. The first one is what we consider to be the more scientific definition, and that is a coherent group of tested general propositions commonly regards as correct that can be used as principles of explanation and prediction for a class of phenomena. Example is Einstein's theory of relativity. The key points for a scientific theory is that it encompasses a large range of related phenomenon, and that it has been extensively tested over time and not proven to be or not shown to be falsified. It has never been falsified. None of the tests came back in a negative way. So Einstein's theory of relativity predicts quite a number of physical phenomenon, from gravitational lensing to gravitational waves to time dilation to length contraction. All of these things have been tested. All of these things have been shown to work in the context of Einstein's theory. The sixth definition is what we most likely think of theory when we talk about it in everyday parlance. For example, I have a theory that Jeffrey Epstein was killed by the Clintons. Sure, that's a theory. Is it a testable theory? Probably not, no. Does it include a large set of phenomena which have been rigorously tested? No, it certainly hasn't. Typically, when people say theory in everyday language, what they really mean from a scientist's perspective is, I have an idea, I have a conjecture. Whether or not, and it's not even a hypothesis really, it's literally that, a conjecture. It is something that really cannot be tested, for the most part. That is what we think of theory in the common everyday language. If you get nothing out of this class, I want you to get this one thing. Nothing in science is proven. If someone tries to tell you that something in science is proven, they're either lying or they're trying to sell you something. Science is provisional. As opposed to, say, astrology, which will tell you, oh, you're an Aries, therefore you have these certain characteristics and there's really nothing you can do about it. Science will say, well, this is how we believe the universe currently works. But we are always open to new ideas. We're always open to the idea that the scientific ideas that we have currently are just not adequate to our understand or to explain the observations that we make. Because we are constantly making new observations, and not just into new fields, but we're making observations with unprecedented precision. And so in both cases, the theory that we have for, say, relativity, which deals with the things in motion, particularly things that are moving very quickly or near a large gravitational mass, even given the new precision, those theories, excuse me, those theories must hold to be true. If they are not, then either the theory must be rejected or it must be revised. Hallmark 1 of science is that it's an exploration. Now, most science, what would be considered hard science or physical sciences, are done through a controlled set of experiments. Astronomy is a bit different in that most of astronomy is done through observational means. We cannot manipulate the subject of our study within a lab. We have to analyze the light emanating from those objects and be clever enough to figure out what that light is doing, why it appears to appear the way it does, and what does that mean about the physical circumstances surrounding how that light was emitted or absorbed or redirected or what have you. So astronomy is more of an observational science than it is an experimental one. Not to say that one is more valid than the other. Astronomy just simply, our laboratory is the universe itself, as opposed to a room in a basement somewhere. The view is much better. So, for example, from an astronomical point of view, Einstein tells us that a large mass, actually, to be perfectly precise, any mass will cause light to bend around it. But only large masses is this even close to being perceptible using the technology that we have, particularly the technology they had at the time. And so this was first observed and tested via an eclipse of stars by Arthur Eddington back in around 1919 or so, or 1921. Can never get those dates right. I think it's 1919. Anyway, what he did was he took measurements of star positions without the sun in that location, and then he took the same measurements with the sun in that location in eclipse. So the sun's light was blocked. He could see the background stars as if it were nighttime. He measured those distances again, and lo and behold, he measured those distances to be slightly larger than if the sun weren't there. And that is precisely what the theory of relativity predicts. Hallmark 2, we are interested in objective reality. We are interested in not only things that we can see and measure and observe, but we are interested in explaining those phenomena through mechanisms which we can see, explain, and observe. So, for instance, science is not interested in topics like metaphysics or religion. We no longer go to Zeus to explain why lightning happens. We are only interested in the physical reality that we can manipulate and observe. Hallmark 3, or as my father would like to say, keep it simple, stupid. Simplicity. Nature is simple. It may not seem that way, but I should say nature favors simplicity. I shouldn't say that nature is simple. That's a gross exaggeration. Nature favors simplicity. If you have two models that equally well explain and observe phenomenon and equally well can predict what that phenomenon will be doing at some later date, then one needs to take the simpler of the two. Best example of this is, and we'll go over this later on, is the Copernican revolution, when we talk about the geocentric universe turning into the heliocentric universe. Copernicus's model of which had the sun at the center was no more or no better at predicting things than the previous geocentric or Earth-centered model, but it was far simpler to use. And so that's what led folks like Kepler to look at Copernicus's model and say, maybe he's got a point. Maybe putting the sun at the center of the universe actually makes things simpler and ultimately will lead to even more and more correct or more precise predictions of the future. And so this is Occam's razor. One of the ways Occam's razor is stated is if two hypotheses explain all observations equally well, then we should use the one that requires the fewest assumptions. So the simplest of the two models. Hallmark 4. As I mentioned before, a hypothesis is only a hypothesis if it produces testable predictions, either now or in the future. If it doesn't, if the model, or if the idea, I should say, cannot be tested in any way that we can currently envision, then it's not really a hypothesis. It's not really in the terms of, or in the realm of what we would consider to be rigorous science. Now, I'm sure there's people out there who are going to argue with me on this, but things like string theory or M theory, this idea of multiple universes, these are interesting concepts. These are interesting ideas, but until they can come up with a way of allowing us to test what something in our universe would look like in the presence of multiple universes, as opposed to the absence of multiple universes, until that experiment can be even designed, these theories, these ideas, or these theories, are really just ideas. Quite fascinating ones, but they're really of no use to science until they can be tested. And then lastly, you have the cosmological principle, which is mostly a principle of astronomy than it is overarching of science. And the cosmological principle is an extension of the Copernican principle. The Copernican principle basically was the one that said, we are not the center of the universe. The cosmological principle states, there is no center of the universe. No place is more important or more preferential than any other place. All places in the universe are of equal significance, either good or bad. The second part of this is that the physical laws which govern what happens on the Earth are the same physical laws which govern what happens on distant galaxies. And this is of vital importance to astronomy because we can't go to these distant galaxies. We have to assume that if I drop Mentos in a Diet Coke bottle in Andromeda, it's going to explode just as it would be here. It would do here. We have to assume that the laws of physics as we understand them today are applicable everywhere in the universe and every when in the universe. Those same physical laws dictate how things move and how things work in the past and also in the future. Without that, the subfield of cosmology is completely up a creek, because without that assumption, without knowing that physics works regardless of when or where you are, we wouldn't be able to make predictions of future events based on what we saw of distant events. So the hallmark of science, the fifth hallmark of science, is the cosmological principle, which states there is no preferential point in the universe, which has the implication that there is no point in the universe where the laws of physics are different than any other point in the universe. Now let's get to the scientific method. The scientific process, which I'm just going to describe, is a very generalized one. Depending on which science you're in, this method can vary quite a bit. But the general framework is the same. For example, astronomers, as I said, primarily rely on observations instead of rigorous experimentation where individual variables are tightly controlled and you have one independent variable. More social sciences rely on surveys. They rely on the construction of very pointed questions in order to get to the answers that they need or answers that they're looking for. They have a hypothesis, and the only way to test that is by asking people questions. Very pointed and very well designed questions, hopefully. So the first part of the scientific method is to ask a question. Is you look out into the world and you say, well, why? Why does that happen? Why does an apple fall from the tree? Why do people like Pokemon? Who knows? You then ask, you then go into background research and ask, have other people observed things falling? And if so, what did they attribute that to? Do other cultures like weird, strange, digitized monsters? If so, what did they do about it? Once you've done your background research, you then construct a hypothesis. You then ask a very pointed question of, for example, does something fall because of its quantity of mass or because of its quantity of density? Or is Mr. Mime the best Pokemon ever? You then create an experiment to determine whether or not you are correct. You design an experiment or set of observations or survey to test whether or not your hypothesis is correct. With the falling example, you can take an experiment where you drop things of the same physical size, but you alter their masses, and you see whether or not they fall at different rates. That keeps the densities the same. Well, you can. I'm sorry. You can take you basically can drop things of the same density but of different masses and see if they fall at the same rate, and that can differentiate between whether or not it's falling by mass or falling by density. You analyze those results and then you publish them, regardless of what your findings are. So if you test your hypothesis and your findings show that yes, indeed, things fall because of their mass as opposed to their density, then you publish that result. You publish that positive result and basically move on. If for whatever reason you got your hypothesis wrong, your data actually falsifies your hypothesis that no, mass actually doesn't affect falling objects at all. It's something else entirely. You publish that as well. That is a null result or a negative result, and that is of equal importance to science because it basically allows people to know that's the wrong way to think about that problem. When other people are asking similar questions and doing their own background research, they might come across your null result and say, okay, well then I'm not going to pursue that line of inquiry because someone else already has and they've shown it not to be the case. And so either yourself or someone else can then say, all right, well, if that isn't the answer to my hypothesis, let me alter my hypothesis to see whether or not I can create another experiment or survey or observation to test whether or not this new hypothesis, given that old result, is in fact the correct one. And that is how science works, is the idea of asking a question, educating yourself about that question as much as you can, constructing a very pointed inquiry that can be tested, creating a test or series of observations in order to do just that, carry those out, analyze your results, and then publish them, regardless of whether or not it's a positive or negative result. That is how science moves forward. Now, occasionally, science undergoes paradigm shifts. For the most part, science, the business of science is to test, retest, and retest. We are looking to see whether or not these the things that we are doing are in fact consistent with the framework of physics that we know today. And we continue to do that until cracks form, until certain experiments falsify our ideas, or at least lead into questions which our theory cannot explain. And that gets us into our next topic, and that is classical mechanics. Because for years, Isaac Newton, the father of classical mechanics, his laws basically described, if you wanted to know how something moved, Newton's laws could do it. It was a time of determinism. Basically, this idea that that scientists believe that, lo and behold, if we have instruments that are precise enough, if we have telescopes that allow us to see far enough, we can determine the universe as a clockwork engine. We know everything that we can. If we know where things are and we know how fast they're moving, we can predict what the universe is going to look like tomorrow, the next day, next year, next century, next millennia, therefore, so forth and so on. It was only until cracks showed up in Newton's theory that Einstein came along and came up with this theory of relativity, which is going to be the subject of the lecture next week. All right, I'm going to pause here, and I will be revisiting this later today in the second half of this lecture.